Okay. Right. So the intermediate value theorem, or what I will often just abbreviate as IVT, kind of comes in two forms. One of those is a relatively basic form, and the second one is the way that your book states it. So I'm going to develop it into the book statement, or derive the book statement via a somewhat simpler statement. That's both from the mathematical standpoint easier to prove, but it's also, I think, more conceptually, from the conceptual standpoint, it's a little bit easier to grasp as well. And then I'll do an example of using it. We'll need it when we get to chapter 3. Really, the intermediate value theorem is going to become important when we get to things like the mean value theorem. When we talk about the mean value theorem and derivatives, we're going to need this, and it's a statement about, or a theorem about continuity. Sorry, it's a theorem about continuous functions, and so kind of falls into this setting here, falls into this section, even though it doesn't necessarily, like, we're not going to see a lot of homework problems on it, and I'm not going to ask you to like memorize the statement, or it might be useful though. Some aspects of some of the examples that we'll see, or the example that I'm going to do, could be useful with some of the homework problems. So let's start with the simpler statement. Okay. So the simpler form of the intermediate value theorem says that if we have a continuous function on a closed and bounded interval, so I'm looking at that interval from, it's important that this is closed and bounded. Right, closed meaning that it contains the endpoints, right? So it contains A and B, so this interval of continuity. Bounded means that neither of those is infinity, right? So as an endpoint of an interval, mathematically, infinity is both, and negative infinity similarly is both open and closed. It has this mathematical property that we call clopin, meaning both open and closed. Here it needs to be closed and bounded, right? So it's just a interval that contains the endpoints, and those endpoints are real numbers. All right, so if f of x is continuous on the closed and bounded interval from a to b, and f of a and f of b have opposite signs, then we know that there exists some value c between a and b, so c is between a and b, such that f of c equals 0. All right, so I can, oftentimes in calculus, right, the statement might be complicated, but if I draw a picture, it makes our lives, or makes our statements a bit more understandable. And honestly, often much of calculus is really, in some ways, putting down, or much of real analysis is taking kind of what we know about drawing functions and trying to put them into words. So that's kind of what we're doing here. So let's say I have my continuous function, this closed and bounded interval, right? I need f of a and f of b to have opposite signs. So let's say here's my a, f of a, all right, and some value down here, that's my b, f of b, right? And I'm going to draw two things here. But first, I'll draw one, and then I'm going to erase it and draw a second thing to make a point. So if f is continuous, right, another way that we can talk about continuous functions is just saying I can draw the function, right, that it both passes the vertical line test, so it only has one value. I mean, that's just something for the vertical line test is what it means to be a function, right? For each input, you have a unique output. You pass the vertical line test, and I can draw it without picking up my pen or pencil, right? So I can take my stylus here and connect the two dots, right? And if I play connect the dots, right, in the kind of the easiest way, right, like that would be my value C, right? Say that f of c equals 0 just means that it's a place where the function crosses the x-axis, right? Because that will have the point c comma of f of c, or c 0, right, since it lies on the x-axis, or the intersection of the function and the x-axis occurs at c. Now, it's important to note that the intermediate value theorem is what we call in math an existence theorem. It is not a uniqueness theorem. So I'll write this off to the side. Right, the IVT is an existence theorem, not a uniqueness theorem. And what I mean by that is also kind of easier to see when I think about a picture here, right? An existence theorem, right? Existence on mathematically means that we have at least one occurrence of something, right? Uniqueness means exactly one, or at most one. Now, when I go back to my picture here, if I want to play connect the dots, draw a continuous function, right, that has those two values that are opposite signs, there's nothing that prevents me from drawing a function that looks like that, right? I mean, that's a perfectly well-defined function as long as it connects the dots, right? But then it has 1, 2, 3, 4, 5 different places that it crosses the x-axis. In other words, 5 values of C between A and B that all satisfy the intermediate value theorem. Right? So the intermediate value theorem doesn't tell me really anything about the exact place that I cross the x-axis. All it does is tell me that there is some place that I cross the x-axis. Right? So I don't know enough really to say that exactly what those C's are. There are kind of some games we can play with the intermediate value theorem by like shrinking the size of our interval to narrow things down. Like if I move B over a little bit and keep moving it and shrink the interval down smaller and smaller, kind of around one of those values of C, making sure that my endpoints stay at opposite signs. I can play a little bit of a game to get myself a good decimal approximation for C, or to help me narrow down what C is. But the intermediate value theorem itself, its basic statement, doesn't really tell me anything about the uniqueness of that of the value C where I cross the x-axis. So I said what we're going to do is take this and generalize it a little bit to get ourselves the definition, or the statement, not definition, the statement of the intermediate value theorem that's in the book. And so let's do that now. So more generally, all right, I can define, or I can state, not define, I can state the IVT as, let's say, given f of x continuous So we're going to be given a continuous function on a closed and bounded interval again. But this time I'm not going to worry about f of a and f of b having opposite signs. I do need a restriction. But the restriction I need is a lot looser. I just need them not to be equal to each other, right? So let's suppose that f of a and f of b aren't equal to each other. All right, so the more general statement, or the way the book states the intermediate value theorem, says that if we're given a continuous function on a closed and bounded interval, so given f of x continuous on the closed and bounded interval from a to b, and suppose that f of a and f of b aren't equal to each other. So instead of them having opposite signs, I just want to know that they're right, that they're not equal to each other. A lot looser. If I have any value z between f of a and f of b, then there exists some value c inside of that interval from a to b such that f of c is equal to z. Right? In other words, right, let's try to look at this pictorially again. So here's my a, here's my b. Let's put a, f of a down there, so that's f of a. Let's let that be f of b. Right? And then I pick out any value z that I want in between there. All right, so let's suppose z is that value. Now z needs to be between a and b. It's important that z is between f of a and f of b. And to find a value c such that f of c equals z, well, f of c equaling z means that it crosses the line, right? I'm looking at that function, right? That linear function y equals z. Right? Y equals z is a horizontal line. Y equals any constant is a horizontal line. And so I can think about my function then, right? If I want to use the intermediate value theorem, right? I'm basically playing the exact same game. It's just instead of crossing the x-axis, now I'm just talking about crossing this horizontal line at y equals z. And I can do it more or less the same way that I did before, right? And so I have, in this case, my example here, 3 different potential values for c. Right, I mean, that gives me a c value. That gives me a c value. That gives me a c value. And if I wanted to translate this back, we can let's say g of x equal f of x minus z. And then what we would be looking at, let's see if I can grab all of that, do what I want. right? G says, well, let's take F and replace it, right? G looks basically like F. I just shifted it down by Z, right? And so just grab, you won't know. All right, so there's our graph of G, right? It's basically looks the same. It looks very similar. Not the same, looks similar. Right? Our A and B values are different. We've shifted them down. All right, but that shifting down just changed. Didn't really change what the graph looks like fundamentally. It just changed where its location was at in the horizontal direction. Right, and so this then satisfies this function over here. It's the difference of two continuous functions, right? Constants are continuous, these horizontal lines. F of x we already said was continuous on that interval, right? And so we know that G is continuous. And now we can go back to the original formulation of the intermediate value theorem about crossing the x-axis, right? To get the result about the same C values, right? And those are the exact same C values we had over there. Right, and so this is the statement that your book has, or that the text has, and is going to ask you some questions about, ask you some related questions. Now, I want to do an example using this, and then we'll be at a good place to finish up. This is really the last thing I want to look at in chapter 2, aside from answering more questions that you all have. And let's look at a proof using the intermediate value theorem. Okay. And our example here asks us to prove that 2 to the x plus 3 to the x equals 4 to the x has a solution. Now, that's not a function, right? I've written down a mathematical expression or a mathematical equation, but it's not a function. So the first thing I need to do is write or find a function that I can apply the intermediate value theorem to. Second thing to notice is when I look at that mathematical equation, 2 to the x plus 3 to the x equals 4 to the x, that's not one that I can easily solve, right? That's not a simple algebra problem. It's not a simple exponential function problem, right? It's not something that I can use my rules from algebra and my rules about exponents to really solve, right? I have x's and exponents. We should know that then, right, when we see x's and exponents, that often means we want to try to do something with logarithms, because exponents inside logs can become constants or become coefficients on the outside, right? And if I tried to apply logarithms to this, right, so if I took the natural log, say, on both sides, right, on the right-hand side, the 4 to the x, I could pull that x out of the exponent and make it a coefficient in front of the logarithm. But on the left-hand side, 2 to the x plus 3 to the x, if I take the natural log of that expression, right, I still have a sum inside of there, and logarithms and sums don't work nicely, right? I don't have a way to evaluate or a way to simplify those, right? Logarithms do not distribute across summations, right? And that exponent, I can't, right? Exponents also don't distribute across sums. And so I really am kind of stuck at some level on the left-hand side with trying to use what we know about our rules for exponents to go through to solve for this value of x. So the intermediate value theorem is really our only, right? I can graph the expression maybe, not really. And I mean, I don't know how to graph that in my calculator on exactly, right? How to graph an equation. I only know how to graph functions. Some of the fancier calculators might be able to graph the solution set or graph the expression, but for the most part, right, I'm kind of stuck. I don't really have a good way to approach that. But the problem isn't asking me, right, find x that solves this, right? It's not asking me for a value. It's just asking me to show that this has a value, right? So to show that this has some solution. And this is actually kind of a common thing that happens in mathematics, right? Is when we encounter mathematical objects or mathematical, good way to say it, mathematical objects, mathematical things that we're investigating, right? Oftentimes we ask ourselves two separate questions, right? One, does it have a solution? And then two, what is the solution? Right? Sometimes half the battle is just saying yes or no. Does it have is this question, does it have an answer? Sometimes it's yes, sometimes it's no. If it has an answer, then we have to go a step further and say, what is that answer? Or can we find a way to represent that answer? But mathematically, those are really two separate things. Does something have two fundamentally different questions? Does it have a solution? And then if it has a solution, what is the solution? And sometimes we can't answer the second question, even if we can answer the first one. This is really one of those cases where I can kind of answer one of the questions, right? And we'll see how to answer it with the intermediate value theorem. But I don't actually know a nice way to represent or find the value. In fact, in this case, the value itself is some transcendental number that really just corresponds to this expression that I wrote up there. So let's go through and see how we can use the intermediate value theorem to approach this. Write it down formally as a proof. So the first thing I want to do is write or find a function, right? Because the intermediate value theorem is about continuous functions. So let's find a continuous function that's useful in solving this. And I'm going to try to take everything back actually to the original statement that I had about the intermediate value theorem about things being equal to 0, right? So I want to look at a continuous function where f of a and f of b have opposite signs. So if I want to try to solve or find a continuous function that I can ask when is it equal to 0? Well, if I have a mathematical expression or mathematical equation like this, right, an easy way to find a related function that I can set to be 0 is just move everything to one side of the function. So I'm going to let f of x be 2 to the x plus 3 to the x minus 4 to the x. All right, so let's just move everything to the left-hand side, right? And if I did that with that equation up here, right, I'd be looking at 2 to the x plus 3 to the x minus 4 to the x equals 0. Okay, I'm in the setup of that. I'm in the setup of the original statement or the first statement I had for the intermediate value theorem. Now, the first thing that I need to show is that I have a function that's continuous on some closed and bounded interval. So let's first just talk about continuity. If I look at this function, it's the sum and difference of a bunch of exponential functions. And we said earlier, right, exponential functions are continuous for all real numbers, and we had a law of continuity, right, that said if I had two functions, f and g, that are continuous, and their sum and difference is also continuous. So if I look at this function, I can first say that it's continuous for all real numbers, right, by saying, since exponential functions are continuous for all real numbers, by the sum and difference law, abbreviate difference as diff, law of continuity, f of x is continuous for all real numbers. Furthermore, what else do I need with the intermediate value theorem? Well, I need our function to be continuous, right? Since it's continuous on all real numbers, right? I can really find, as long as I can find values of a and b, I'll know that it's going to be continuous on that closed interval from a to b. But I need f of a and f of b to have opposite signs. So I need to find two values a and b that when I plug them into the function, I get out values with opposite signs. Let's pick some easy values. F of 1 is an easy one because that's just 2 to the first plus 3 to the first minus 4 to the first. Well, that's 2 plus 3 minus 4. So that's 5 minus 4 is 1 is bigger than 0. And now I need to find a value that's negative, and so I need to make this 4 to the x bigger. And since 4 is bigger than 2 and 3, this 4 to the x as an exponential function is going to grow faster than 2 to the x and 3 to the x. So I just need to pick a bigger value for x. And in this case, 2 actually works because 2 squared plus 3 squared minus 4 squared, right? That's 4 plus 9 minus 16. So 13 minus 16 is negative 3, is less than 0. So I'm looking at the interval from 1 to 4. Sorry, not from 1 to 4, from 1 to 2. Right, that's going to be my closed and bounded interval. And I know by what we had from exponential functions and the laws of continuity that f of x is going to be continuous or is continuous on that closed and bounded interval. Right, so then we get by the intermediate value theorem, there exists some value c such that f of c is equal to 0. So some value c between a and b. Right, so intermediate value theorem tells us then there exists some value c between 1 and 2 such that f of c, which is 2 to the c plus 3 to the c minus 4 to the c is equal to 0, right? Or equivalently, right? If I take the 4 to the c and move it to the other side, right? I know that 2 to the c plus 3 to the c is equal to 4 to the c. Okay. Right, so when we were writing up the proof, right, I needed to make sure that I satisfied all of those initial conditions. So I had a continuous function on a closed and bounded interval. The endpoints of the interval, when I evaluated those in the function, had opposite signs. Right, I had to show all of that first. But once I've shown all of that, right, I get that conclusion. that there exists some value c such that f of c is equal to 0. That's what we got there. And to explain why our function was continuous on this closed and bounded interval from 1 to 2, show that f of 1 and 2 have opposite signs, right? But then the intermediate value theorem, right, gives us a value. Well, it doesn't give us the value, but it gives us the existence of a value c between 1 and 2, where f of c is equal to 0. Like I said, the intermediate value theorem doesn't tell me what c is. All I know is c is somewhere between 1 and 2. That's as best as I can really say. Okay. Comments or questions on that? It's kind of one of the first abstract proofs that we've looked at this semester. So I know that may be a little bit more we've seen in a previous math class, but I'm going to have a couple of, right, when the proofs are simple enough or when some examples lend themselves to proofs that are simple enough, we will look at those, especially because math majors will need to have a bit of familiarity with these as we get into, or as you start approaching, say, courses like discrete math in the spring semester, which is all about proving simple statements and different types of proofs. So questions, comments in general then, if nobody has any questions or comments on the example. Okay, so we got about 5 minutes, but this is a good place for us to stop if nobody has any questions.